We present our work, Temporal Feature Alignment and Mutual Information Maximization for Video-Based Human Pose Estimation. In this work, we study human pose estimation in videos, whereby we seek to make use of additional contextual information to improve the detected poses in the keyframe. Some common challenges of video-based pose estimation arise due to fast motion and pose occlusion. Current methods directly aggregate unaligned context across frames, resulting in misalignment between pose features of the current frame and neighboring frames. More importantly, existing approaches build upon a straightforward pose estimation loss, which unfortunately cannot constrain the network to fully leverage useful information from neighboring frames. An overview of our approach is as follows. We first extract the features for a human subject on a keyframe and supporting frames using a backbone network. Such a backbone network is pre-trained for single pose estimation. We then perform a two-stage transformation to align the supporting frame features with the keyframe feature. This comprises of a global affine transformation, whereby the network module estimates the affine transformation parameters to align the features, followed by a local calibration module that further performs meticulous fine-tuning at the pixel level to align the features. The local calibration module makes use of modulated deformable convolutions and learns location shifts and intensity fluctuations of the supporting frame features with respect to that of the keyframe feature. Subsequently, we aggregate over aligned supporting frame features and the keyframe feature via element-wise addition to obtain an enhanced feature. This is then fed to a detection head that outputs post-estimation heat maps and is optimized by a heat map loss. Another key element in our approach is that instead of merely depending on the heat map loss, we introduce supervision at the feature level. In order to highlight the purposeful additional information from the supporting frames, we propose a mutual information objective, which seeks to maximize the amount of complementary information in the enhanced feature. Mutual information is a measure of the statistical dependency between random variables. In our case, we seek to maximize the task-relevant information in the enhanced feature, which is not present in the keyframe feature. We factorize our mutual information objective, and the last term in pink corresponds to task-irrelevant information. We may discard this term since the task-specific information is expected to dominate upon sufficient training. Therefore, our mutual information objective is approximated by the dependence between the label and the enhanced feature, minus the mutual dependence of the features. We also introduce two regularization terms to alleviate information dropping. Simultaneously minimizing these two terms will prevent excessive information loss from the supporting frame and keyframe features. Overall, our framework is summarized as above. We benchmark our approach on the PostTrack 2017 challenge, achieving the top performance for both the validation and test dataset. Likewise, for the PostTrack 2018 challenge dataset, as well as for the sub-JHMDB dataset, our approach is able to consistently achieve new state-of-the-art performance across all three datasets, demonstrating the effectiveness of our proposed feature alignment and mutual information objective. Our approach is generally more robust in challenging scenarios involving rapid motion and pose occlusions, delivering more accurate pose estimations than existing methods. Finally, we showcase some extended results on videos. To summarize, we examine the multi-frame human pose estimation task from the perspective of effectively leveraging temporal context through feature alignment and complementary information mining. Our method is able to better handle challenging scenarios in videos, and extensive experiments confirm the effectiveness of our approach. Thank you.